Okay, let's talk about L'Hopital's rule. We're not going to precisely prove this. We'll kind of explain why the proof works a little bit, but we're going to see some examples and see how to use this. The book doesn't go into that too deeply. The proof's kind of technical in itself, but we can kind of get an idea of how it works using the mean value theorem. Okay, so let me state the L'Hopital's rule theorem first. So the theorem is let f and g map the open interval from a to b into R be differentiable functions, and we want them differentiable on the entire interval from a to b. If I have an f and a g which aren't differentiable on an entire interval, but I'm trying to take a limit at a, I can just shrink that interval down small enough so that it's differentiable in that little interval. So we can choose a and b freely. F can be kind of restricted to a smaller domain if we need to. And we need some more assumptions, and we want g of x not equal to 0 on that entire domain. So this could be another reason why we might have to shrink that domain down and restrict a and b a little bit. Okay. Then, if one of two things happens, one, the limit as x goes to a of f of x equals 0, and that's also equal to the limit as x goes to a of g of x. Or the second thing that could happen is that the limit as x goes to a of g of x equals plus or minus infinity. So either g of x gets really, really big, or they both get close to 0. So if either of those happens, then the limit as x goes to a of the ratio of x over g is equal to the limit as x goes to a of the derivatives. So f prime over g prime of x when it exists. So if this limit exists, this limit is equal to the same thing. Okay. Note, we could replace, instead of x going to a and all of these things, we could replace it with x going to b. So let me show you a quick example first, and then we'll kind of talk about why it's true a little bit, and then get into some more examples. So, sort of easy example to start with. So maybe I want to compute the limit or find the horizontal asymptote of this rational function. So I want the limit as x goes to infinity of, say, 2x squared plus 3x minus 7 over 4x squared plus x plus 3. Say I want to find the horizontal asymptote in my algebra class. Well, they don't know calculus, but for you, to make it easier, how would you do this in a calculus class? Well, we can use L'Hopital's rule, because if we take g of x equal to 4x squared plus x plus 3, then the limit as x goes to infinity of g of x equals infinity. So situation 2 is satisfied in L'Hopital's rule, right? Situation 2 was the limit of the denominator goes to infinity. So we take the numerator to be f, and that's 2x squared plus 3x minus 7. And then this limit, x goes to infinity, of 2x squared plus 3x minus 7 over 4x squared plus x plus 3 is equal to the limit of their derivatives, which would be 4x plus 3 over 8x plus 1. Okay, and I run into the same situation again, and we repeat. Repeat using LHopital's rule, so this is now equal to the limit as x goes to infinity of the derivative of the numerator 4 over the derivative of the denominator 8, so 1/2. Okay. One of your rules from algebra usually is just look at the leading coefficients. If the degrees are the same, the leading coefficients give you this ratio. Great, everything worked out fine. Let's see, why is LHopital's rule true now? Sort of a sketchy proof. Okay, so I've got this number line, and I've got this endpoint A, which things are getting close to, and this endpoint's B. So let me look at the limit of f prime at x over g prime at x as x gets close to A. Well, this is sort of the limit f of t minus f of x over t minus x over g of t minus g of x over t minus x, and these are limits as t approaches x, and this is a limit as x approaches A. So I got sort of this big mess of stuff going on. Since these limits are the same, I'm going to use the quotient rule. I'm going to put them into the same thing. So this is the limit x goes to A, limit t goes to x of, and when I do that I can kind of flip and multiply and cancel out that t minus x. So I get f of t, well, let's not do the cancel out the t minus x, f of x over t minus x over g of t minus g of x over t minus x. Okay. Now, the mean value theorem says, well, if, let's say this is x and this is t, as t is approaching x, the mean value theorem, I can take this thing, which is the mean value between t and x, I can find some c in here where this is equal to limit as x goes to A, limit as t goes to x of f prime at C, and there's also a we'll call it D in here, where we use the mean value theorem on the bottom, and g prime at D. Okay, so the mean value theorem kind of gives me that thing. And then let's look at this left hand side, and now let's cancel things out a little bit. So I've got the limit, so we're going to kind of rewrite this line. We've got the limit x goes to A and t goes to x of f of t minus f of x over t g of t minus g of x. And that's going to equal limit as x goes to a and limit as t goes to x of f prime at c over g prime at d. And c and d are between sort of t and a for sure. Okay. So what happens here? Well, by assumption, either this denominator gets really big. Let's kind of not worry about this case. Let's worry about case 1. Case 1, this goes to 0 and this goes to 0, right? So what we're doing is we're taking the limit of f over g and we're getting it to be the limit of f prime over g prime. So that's sort of what happens. This, in the long run, turns into the limit because t is getting closer to x and x is getting closer to a. This is the limit as t goes to a of f of t over g of t, since these guys go to 0. And this side is equal to the limit as, well, c is between t and a, and so c also has to go to a, and g is between, or d is between t and a, so d has to go to a, and so this is also the limit f prime at t over g prime at t, sort of by continuity again, as t goes to a, and that's where we get our LHopital's rule, if this exists. Okay, that was pretty hand-wavy and kind of technical, and it doesn't actually prove anything. We haven't sort of gone through the gritty details about this, but that's kind of the idea about what goes behind LHopital's rule. You kind of do this algebra in the middle, and you use the mean value theorem and kind of trap the mean value between the values that are going towards a. Okay, so let's talk about LHopital's rule in practice. So LHopital's rule, in most textbooks, you get to use it with indeterminate forms. And the two common indeterminate forms, the two sort of base ones, the ones that we get directly from the definition of LHopital's rule, are 0 over 0 and, well, something over infinity. So the only way that something over infinity is sort of unknown to us as a limit, well, if you're dividing by something that gets obscenely large, it's going to get small if it stays finite. So the only thing that's sort of unknown to us is if you've got another infinity, and it could be a plus or minus infinity over an infinity type thing. So these are kind of our two base forms of indeterminate forms, using just right here, this is your 0 over 0 form, and this is going to be your infinity over infinity form. We can use it when there's something not infinity on top, but the only time that it's sort of indeterminate is if it's infinity over infinity. Okay, so we get to use these two indeterminate forms to use LHopital's rule, and those are our common ones. We saw the example earlier where I had infinity over infinity. And then there's sort of the unusual indeterminate forms. And these are the ones I want to talk about today. So there's 5 of them. There's 0 times infinity. There's infinity minus infinity. There's 0 to the 0. There's 1 to the infinity. and finally there's infinity to the 0. So if you multiply something really close to 0 by something really big, we don't really know what's going to happen. Which one sort of outweighs the other? Who knows? You take something really big away from something really big, don't really know. You take something really small to a really small power, we don't know what happens. I take something really, really close to 1 and multiply it by itself a whole bunch of times, we don't really know what's going to happen. Or if I take something really, really big and I take a really, really big root of it, we don't know what happens. Those are kind of the ideas behind each of these 5 indeterminate forms. And our goal is to turn these into one of our regular indeterminate forms. And we use the continuity of limits to do that. So let's see an example of this first one. So for the first one, let's do this as an example. Let's take the limit of x going to 0 from above, x cubed times the natural log of x. Why is this infinity times 0? Well, as x gets close to 0, when I put it into a natural log, the outputs of the natural log get close to negative infinity, right? So this kind of looks like negative infinity, and if I take 0 and I raise it to the 3rd power, I get 0. So it looks like 0 times negative infinity is close enough to 0 times infinity for us. How do I put this into the 0 over 0 form or the infinity over infinity form? Well, there's a couple ways to do that. I can either put it into 0 over 0 by dividing by the infinity form. I can take this as 0 divided by 1 over infinity, and that's 0 over 0. Or I can put it into infinity over infinity form by taking infinity times 1 divided by 1 over 0, and that equals my infinity over infinity form. So let's do the second one. So let's take this, and this is going to equal the limit as x goes to 0 from above of the natural log of x divided by 1 over x cubed. Okay. Multiplying by x cubed is the same as dividing by the reciprocal of x cubed. Now I've got this as infinity over infinity, and we can use LHopital's rule, and this is going to be the limit as x goes to 0 from above. The derivative of natural log of x is 1 over x. The derivative of 1 over x cubed is negative 3 divided by x to the negative 4th. Okay. Sorry, divided by x to the 4th. And now I can just do some algebra. So I've got the limit as x goes to 0 from above. If I flip this over, I get x to the 4th over negative 3x, which is the limit x goes to 0 from above. I could use LHopital's rule on that if I wanted, because it's a 0 over 0, but I'm just going to do some simple algebra. I get x cubed over negative 3, and that's going to be 0 because that's a continuous function. I can just plug in 0 into that function and get my limit out. Okay. So the 0 times infinity form is fairly straightforward to get it into 0 over 0 or infinity over infinity. These other forms we have to do a little bit more work with because, well, multiplication and division are really closely related, so changing multiplication and division is easy. Subtraction, exponentiation, they're not quite as easily tied to division. So somehow I have to take these and change them into a division problem, so I get 0 over 0 or infinity over infinity, we're going to use exponentiation and logarithms to do that. So let's move on to the next form that we want to work with. Let's do infinity minus infinity. So let's take the limit as x goes to 0 of 1 over x minus 1 over the natural log of 1 plus x. Okay, why is this infinity minus infinity? Well, as x gets close to 0, 1 over x goes to infinity. So this looks like infinity. And then I've got a subtraction. And the natural log of 1 is 0. And so as x gets closer and closer to 0, this denominator on this side gets closer and closer to 0. And dividing 1 by something that gets closer and closer to 0 looks like infinity as well. So how do I change subtraction into division? Well, we can find a common denominator if we wanted. And there's another way too, but let's do the common denominator first, and then we'll do the other way and see two ways to do this. So let's look at this. This looks like the limit as x goes to 0 of natural log of x minus, natural log of 1 plus x minus x divided by x times the natural log of 1 plus x. Now I've got 0 minus 0 over the denominator goes to 0. So now I've got 0 over 0. Okay, let's finish this off then. We can take LHopital's rule. I got the limit as x goes to infinity, 1 over 1 plus x minus, well, the derivative of x is 1, and then down here I'm going to have to use the product rule. So I've got x over 1 plus x plus natural log of 1 plus x. And in this case I see that I have 0 over 0 again, but let's do some algebra. And I'm going to multiply everything by 1 plus x, top and bottom. If I multiply the top and bottom by 1 plus x, I get 1 minus 1 plus x divided by x plus natural log of 1 plus x. Okay, this simplifies a little bit. This is the limit. X goes to not infinity for my x goes to 0, and up here I've got negative x over x plus natural log of 1 plus x, which is 0 over 0 again. So we use LHopital's rule again, and then I get negative 1 over 1 plus 1 over 1 plus x, and that's as x goes to 0. Now this is a continuous function. If I just take x equal to 0, I get negative 1 over 2. So negative 1/2 would be our limit. Okay. There is another way to do this. So let's see if we can do this again. X goes to 0 for your infinity minus infinities, and that's to use exponentiation. So if I use exponentiation, let's rewrite this. I've got 1 over x minus 1 over natural log of 1 plus x. And I'm going to call this equal to L. And this is going to be kind of the trick we use for the other ones too. So assume that this limit exists. Then e to the L, I can exponentiate this. I'm going to use e because I've got a natural log in there, so I should probably use the same base for my logarithm and my exponential. That's going to be equal to e to this limit as x goes to 0 of 1 minus x, 1 over x minus 1 over 1 times natural log 1 plus x. There we go. And now e is a continuous function, and continuous functions and limits work nicely with each other. So I can take this and say it's the limit as x goes to 0 of e to this stuff. Okay. And exponentials and subtraction, they turn things into division. So this is now the limit as x goes to 0 of e to the 1 over x divided by e to the 1 over the natural log of 1 plus x. And now what I've got is e to something infinite. This is now infinity over infinity, so I could use LHopital's rule on this. Okay, this instance probably wasn't the best method for that because this chain rule and this exponential, they're going to be kind of messy. So for this problem, our first example was probably better, but this is another way we can change infinity minus infinity into infinity over infinity. So I'm going to stop there. We've already proved that problem once. Let's go to another example, and we're going to use kind of the same method as that. We're going to say, suppose it's equal to this, and then go from there. So let's do this guy. Compute the limit as x goes to 0 of 1 plus 1 over x to the x. Some of you might recognize this. This is one of our common limits. This is going to equal e to the x. Or sorry, e to the 0, because x is going to 0. So this is going to be 1. No, sorry, this should be. Let's go to infinity. And then now this is going to be e. Okay. So LHopital's rule, what does this tell me? This looks like our form of 1 to the infinity. So this is a form that we need to somehow get into a division form. So right now I've got an exponential. I want to change it into division form. So it'd be nice to be able to bring the two parts of the function, the exponent, which goes off to infinity, and the base, which gets close to 1, into sort of an f over g type situation. Or I should be able to take the exponent times the base somehow. Well, that sounds like I need to get a logarithm in here. So what we're going to do is we're going to take, let's say, suppose L is equal to this limit, 1 plus 1 over x to the x. Then the natural log of L is equal to the natural log of the limit. And because the natural log is a continuous function, limits and natural logs play nicely. So this is the limit as x goes to infinity of the natural log of 1 plus 1 over x to the x. And now we can use logarithm rules. This is the limit as x goes to infinity of x times the natural log of 1 plus 1 over x. And now I've got sort of an infinity times infinity situation. And I can change that into, not an infinity times infinity situation, an infinity times 0 situation. If it was infinity times infinity, the limit would be infinity. So I've got something really big times something really small. We don't know how those are going to act. Now I can change this into an infinity over infinity or a 0 over 0 situation. Let's rewrite it then as the limit as x goes to infinity of, I'm going to write it as a 0 over 0, so the natural log of 1 plus 1 over x divided by 1 over x. Now I've got a 0 over 0 situation. We can use LHopital's rule. Okay, and LHopital's rule tells me this is going to be the limit as x goes to infinity of, well, the derivative of that, I'm going to have to use the chain rule. So it's 1 over 1 plus 1 over x times the derivative of the inside stuff. So that's going to be negative 1 over x squared, and then divided by negative 1 over x squared, which is the derivative of the denominator. Those will cancel. This is the limit as x goes to infinity of 1 over 1 plus 1 over x. As x goes to infinity, that goes to 0. This is equal to 1. Okay, so that tells me the natural log of L is equal to 1. We want to know what L is, so L equals e to the first, or just e. L equals e, which is the limit of 1 plus 1 over x to the x. So we use LHopital's rule to show that sort of standard limit as x goes off to infinity. So using the trick of continuity and exponentials or logarithms is how we change forms. So here we used an exponential and continuity to change to a infinity over infinity form. Here we used a logarithm and continuity to change to a 0 over 0 form. So let me just kind of state what you would do for those other indeterminate forms. The other indeterminate forms we had were 0 to the 0. We did a 1 to infinity. We did a 0 times infinity. We did a infinity minus infinity. And the other one we had was a infinity to the 0. We've seen the other ones. So for this one, what I would probably do is, so you've got f of x and g of x for both of these. We're going to take this equals L. I'm going to take the natural log of both of these. So the natural log of L is equal to, well, since natural logs and limits play nicely, this is going to be the limit as x goes to a of g of x times the natural log of f of x. And in the 0 over 0 to the 0 case, g of x goes to 0. The natural log of the base, the f of x, this would go to negative infinity, so you end up in the 0 times negative infinity case, or the other case, if you're doing this one, the exponent is 0 and the denominator, or the base, f of x goes to infinity, the natural log of infinity goes to positive infinity. So you end up with 0 times infinity or 0 times negative infinity, and from there you use the trick that we divide by 1 over g of x, so you get the natural log of f of x over 1 over g of x, and you end up in the infinity over infinity case with a plus or a minus. Okay, so those are how we use LHopital's rule, and a little bit about the proof of it